Hello, and welcome to Astronomy 100. In this video, we're going to continue our discussion of galaxies. In our last video, we described how the Milky Way is something that when you go outside, you can see it stretching all the way across the sky, and it becomes very obvious that we are inside of this thing called the Milky Way. But astronomers throughout history were more curious about the details. What was its shape? What is its size? What would it look like from the outside? And so in the last video, we started to describe how we can start to piece together the idea of the shape and the size of the Milky Way galaxy, and more importantly, where the sun is located in the galaxy. So let's continue with our discussion related to those particular topics. So as we saw in the previous video, that the Milky Way itself is something that we are inside of. The next question is what is more of the details about the shape of this thing that we call the Milky Way galaxy? Now, there's a way we can do this from the inside out. The analogy that I like to give is if you were stuck inside of your house, let's say you were unable to go through the doors or the windows, you could never go outside. You could still figure out what your house would look like from the outside if you just were able to measure all the things about the inside. How far to each wall, how far to the ceiling, how many floors, how big is the bottom floor, how big is the top floor, and you could probably sketch an image of what your house would look like from the outside. Well, it's the same way in astronomy. Here is the location of the sun. And so what we can do is from the surface of the Earth, we can send out signals into space, or we can receive signals from space. And because it takes a long time to send anything out to measure distances, we have to wait for light from various objects to come to us. So one of the things that we can do is we can actually use radio telescopes, and radio telescopes have the ability to measure the energy that comes from hydrogen. Now notice this says neutral hydrogen, and what that simply means is this is hydrogen that is not excited. It is hydrogen that's not energized. But what happens is a complicated set of things occur inside of every hydrogen atom where a certain amount of energy will be given off by the hydrogen itself based on how the electron is orbiting around the nucleus. And so there's a certain type of radio energy that comes from all neutral or unexcited hydrogen atoms. And using radio telescopes, what we can do is basically point them all over the sky, and we can measure that radio energy coming from the neutral hydrogen. And so what we can piece together, essentially we get the light coming from this direction, the radio light from that direction, the radio light from that direction, and so forth. And as this light comes into our location, what we can do is we can figure out where all the clouds of neutral hydrogen are. So essentially, we're seeing the hydrogen in our galaxy by the radio light that the neutral hydrogen produces. And what I want you to notice is from our location, the light that comes in seems to start to trace out some structural details when it comes to our galaxy. Notice there's a whole bunch of neutral hydrogen like this, and then there's nothing right here, and then a whole bunch of it like this, and a whole bunch right here. You can see gaps and you can see large gatherings, and notice the shape, the curvature of each of these large clouds of neutral hydrogen. Starts to piece together an image of what our galaxy looks like from the inside out. It's sort of like radar. If you use a radar instrument to figure out where all the clouds are, you can start to get a feel for the shape of the storm system that's about to move over you by simply looking from your location using radar. Another technique, a very similar technique, is we can look for the various collections of things in our galaxy. In other words, look for where all the objects are and how those objects are gathered. So the sun's location is right here. And when we use telescopes to do surveys, we look for a variety of things. For instance, this symbol right here are all of the open clusters. An open cluster, if you recall from a previous video, is just a cluster of stars moving together through the galaxy. And then what you can also see is what are called H2 regions. These are clouds of excited hydrogen. And so basically, when you start to look at where are all the clusters, where are all the clouds of hydrogen gas, and so forth, you can see that when you survey, when you look for all of these objects and find their locations, essentially mapping where all of these types of clusters and clouds of gas are, you can easily see the groupings of all of these particular objects seems to suggest that we have a galaxy that is actually a spiral-shaped galaxy. And these spiral shapes are what we call spiral arms of the galaxy itself. And so by measuring where all the objects are and how they're collected and where the various other types of material is in the Milky Way, we can now come to the conclusion that our galaxy that we belong to is a spiral galaxy. If you could be outside of it, looking back down on top of it, so this is the top-down view. If you're hovering over it, you would notice that the Milky Way would have this particular spiral shape to it. And this picture, although it is just an artist's illustration, because remember, we have never been outside of the galaxy to take a picture of it, this is an artist's impression of what our galaxy would look like if we could leave it. This is not just artistic license. This and all of the information in this particular illustration is accurate based on our measurements. So the Milky Way galaxy has spiral arms that are shaped exactly like you see here. Notice this spiral arm branches into two separate spiral arms. That is accurate. And again, another branch here. So what we have is the particular shape and structure of our galaxy portrayed by studying it from the inside out. And the sun's location is right here. If you remember from the last video, it was Harlow Shapley that was able to figure out that the center of the galaxy is in the direction of Sagittarius, and our distance from the center is about 28,000 light years. So the distance from right here all the way to right here is 28,000 light years. And so by studying it, we now know that the Milky Way has several prominent spiral arms. Each of them is labeled. These are the names, officially the names of the spiral arms. And the names happen to be with the constellations in the direction that you happen to look to see these particular regions. Now, a sense of scale, this little white bar down here is 10,000 light years. So you can see that it's about 10, 20, almost 30, 28,000 light years to the center of the galaxy. So we now know that the Milky Way galaxy, our home, is a spiral galaxy, and it is flat with a spiral shape to it. And then the last thing is, in the last 20 years or so, we have become quite aware through observation that our galaxy type is called a barred spiral galaxy. This bar that you see right through the middle of the galaxy is a collection of stars and some gas and dust, but this shape and this bar is actually real. So our galaxy would look just like this, a barred spiral galaxy, if we had the ability to look at it from the outside. Let's say somebody else in some other galaxy looking up in the sky, looking at our galaxy. Now let's look at some of the details. This, let me go back for a second. This is the view looking down, the top-down view. So what that means is if you were hovering over the top of it, looking down on top of it, of course, from the top-down view, this is what you would see. This is what we call the edge-on view. So the idea is that if you could look at it from the edge, you would see this. And if you could look at it from the top, you would see this. Okay, so this is the edge-on view. Notice that the Milky Way has a thicker center to it and a tapered off region that surrounds it there. So let's go through some of the details of the names and what you would find. The size of the Milky Way galaxy, if we were to go from one side of the disk all the way to the other side, it would be about 100,000 light years. So traveling at the speed of light would take you about 100,000 years to go all the way across from one side to the other. And the thickness of the galaxy obviously varies. You can see it's thicker in the middle and thinner on the edge, but an average thickness right about where the sun's location is, the sun is located right here, the thickness is about 3,000 light years. So that's the thickness of the galaxy based on our location. We break the Milky Way galaxy down into 3 distinct regions. The part that is near the center is called the galactic nucleus, or the nucleus of the Milky Way. In the nucleus of the Milky Way, we find lots and lots of very old stars. These are stars, in some cases, that have been around since the formation of the Milky Way galaxy itself. These stars tend to be a lot more red in their appearance, and that's why the center of the galaxy has a bit of a reddish, whitish glow to it when you see pictures of it in the sky. Then we have the disk of the Milky Way. So you'll notice that the flat part from side to side all the way around is called the disk. In the disk, we tend to find some of the youngest stars in our galaxy. So brand new, newly formed stars are found out in the disk. The sun's location is also in the disk of the Milky Way galaxy. And then we have what is referred to as the halo of the galaxy. The halo is everything above or below the galaxy. And the halo is the home to all of those globular clusters. So if you're outside of the galaxy above it, or outside of the galaxy below it, you are in what's called the galactic halo. And what we tend to find in the galactic halo are some of the oldest stars in our universe. Globular clusters are home to very, very old stars. Some of the stars in globular clusters are 12 billion years old, almost as old as the universe itself. So the halo is the home to where you find most of the very old stars. Now, when it comes to the movements of stars, the nucleus of the galaxy, what you have are movements of stars shown by the arrows that you see here on the screen. So you have stars that go below, around, and above. So essentially they can go above and below all the way around. They're not really confined to a flat space. They can go above, below, or through and around. There's just sort of a chaotic movement in a very circular fashion. And then out in the disk, what we know now is that the stars out in the disk have a bit of an up and down undulating movement. The sun, as it moves through the galaxy, goes below and then rises above and then goes below and then rises above. And sometimes we call this the merry-go-round effect or a carousel effect. If you've ever seen a carousel where the horses rise and fall as the carousel turns, it's very similar to that. So the sun goes through the galactic plane, through the disk, then it goes above the disk, and then it goes through to the bottom below, so above and below and above. It's kind of an interesting thing. The movement is not just around the disk, but it kind of goes up and then down and then up and then down as it goes around. And just for pure numbers' sake, when it comes to the sun, based on the sun's location, the sun takes about 220 million years to make one trip around the galaxy. So if the sun were to start today on its next journey, its next lap, it'll come all the way back to where it is today in about 250 million years, about 220 million years to make one trip around the Milky Way galaxy. And then out in the halo, the movements of the stars and the clusters in the halo again becomes more spherical. So notice the stars are not moving in the disk, but they're going above and below, surrounding it, as if they're orbiting around the entire galaxy itself. So different types of movements of different types of stars in the disk of the galaxy. Now, one of the other questions, of course, related to this is why does the Milky Way galaxy and other spiral galaxies, why do they have spiral arms? What is the cause of this? Is this something that has been the case from the very beginning, or is there something that is causing a galaxy to have the spiral arms that we see? It's a little bit of a complicated idea that we'll get into in the next video because we're just running a little bit short of time to get it into this video. But the idea of why the Milky Way has a spiral shape is one that was a little controversial, a little confusing, but we think we've got it worked out, that we'll save that for the next video. I hope you'll join me.